by evaluating these functions at this point. Yes?
In your experience with computational math and such, is this the basis for UV mapping and three-dimensional models and such?
UV mapping? Is that?
Well, you may not be exposed to that. That's more of an animation field.
It's quite possible. It depends on what their notation is.
Texture mapping, pretty much. 2D texture to a 3D object.
Okay, yeah, then probably is something like that. Because U and V are normally used for variables when you're parameterizing a surface, just like we normally use T for curves. All right. Now, here's an example of a parameterized surface. So we let U go between 0 and 2 pi, and V go between -1 and 1. So then X is equal to 1 plus V over 2 cosine, yep, U over 2 cosine U. Y of UV is 1 plus, so it starts out the same way. And then we have sine U, and then Z over 2 sine U over 2. Now, it's not at all obvious what this surface looks like when you plug in points UV from these intervals and see what X, Y, and Z are. But what you get is called a Mobius strip. Okay. And it's a surface with one side. So it looks kind of like, well, actually, I'm not going to draw because I've already put a picture in the notes. It's on page 2.
It's an impossible object, though, isn't it?
No, I'll show you. You can make one. All right. So you just take a strip of paper. That part should have taken a longer one. Yeah, let's take a longer one. All right. Okay, so then you twist it, and then you attach it. Now, if I was thinking ahead, I would have brought some tape.
You did not foresee this.
I actually was going to do this, but I just was lazy. And so then what you can do is, then if you take a pen, that I do have, and you start writing at this point, and you keep going around, even though you're staying on the same side, and I swear I'm not cheating here, no matter how awkward I am with the pen, but you're going to end up back where you started. So you can keep following around here. So now it looks like I'm on the other side, but I've never switched sides. So I come back to the beginning. And this hasn't worked out so well because I'm trying to write on a awkward surface. What? All right, that works. Oh, okay. I'll try not to break it. Okay. Ah, that's a green staple too. Okay. So.
Why does it say that it only has one side, though? Like, well, what does that mean? When looking at it here, there would still be the back side of the paper, right?
No, because you can draw a line along the paper, and I'm never switching sides, and I can end up back where I started.
But you could do that if you just folded it like regular without the twist.
Well, in that case, the surface would have two clearly defined sides if you keep writing. So if I don't twist and I start writing along, I will come back to where I started, but there's another side of the paper that never had anything written on it. Here I've covered the entire thing. Every portion of it has a line going down the middle.
Okay.
Yeah. So so in this case, because most surfaces, like something like this, has an orientation to it. It's called orientable. So you can define a normal vector pointing always in this direction, or you can negate it, and then it's pointing the other way. But here, there's only one normal vector that covers everything. So it's one of the common counterexamples, because it's tempting to assume, oh, every surface has an orientation to it, but this is an example that doesn't. All right. Now, if you're familiar with the artist M.C. Escher,
I
Yep.
saw about it.
What?
I said, man, that looks like something Escher would do.
yeah, and he did. He did one of his works has a Mobius strip, where he has the surface, and it's kind of has it drawn kind of like ladder-like, and he has ants. These really big, gross ants crawling all over it. So. All right. So what's interesting is this is one way to describe a surface using parametric equations. Another way to describe surfaces is this way. A function of f of x, y, z is equal to 0. So for instance, you want to describe the unit sphere. So x squared plus y squared plus z squared minus 1 is equal to 0. Now, we know how to describe a sphere this way, and we know how to describe a sphere using parametric equations, because we can use spherical coordinates. So most surfaces can be described either way, using parametric equations or as a level set of a function of 3 variables. But the Mobius strip is different. We have parametric equations. You cannot find a function, f of x, y, you cannot come up with an equation f of x, y equals 0 that the Mobius strip satisfies because of that non-orientability. You have to go parametric in that case. Okay. Here's another example. Another kind of surface to deal with is called a surface of revolution. Remember solids of revolution from 168? Disk method, shell method, all that good stuff? So back then you were using those methods to compute volumes of solids of revolution. Similar idea can be used to compute areas of surfaces of revolution. So we have this equation for a paraboloid. We've actually seen this example in another context. So we have a paraboloid, something like this. All right. And we're going to impose that x is between 0 and 4. Now, this curve right here, running along the top of a paraboloid, this is z is equal to the square root of x over 4. And this curve down below, that's the curve z is equal to minus square root of x over 4. Because in both cases, y is equal to 0. So then you can figure out what these curves are from looking at the original equation. Now, it'd be nice to come up with parametric equations to describe the surface, and here's one way you can do it. You can let x be one of the parameters. So x is just going to be x, and then you can use polar coordinates for y and z. So y, given the fact that y squared plus z squared is x over 4, so y is going to be the square root of x over 4, cosine theta. Z is square root of x over 4 sine theta, and theta runs from 0 to 2 pi. So a surface of revolution like this that you get by taking some curve in the plane and revolving it around an axis can be described using this kind of parametric equation, where the independent variable of this function is one of the parameters, and then the other parameter is the angle theta. Okay. So what you get is something like this.